So next thing we want to do is generalize this to more than one dependent coordinate. So for example, we could have that f is actually equal to f of y, y prime, z, z prime, x, or this is equal to f of, let's write it this way, yi, which depends on x, y prime I, which depends on x, and x, where then I runs from 1 to all the way out to n number of expressions, n number of dimensions, for example. So we want to see what happens to Euler equations when we have more than one dependent coordinate. So basically, we're going to do exactly the same thing we did before. So what we're going to do here is we're going to take yi, we're going to reparameterize this in terms of alpha, where this is equal to yi, x evaluated alpha is equal to 0, plus alpha then times some arbitrary function, where we can have a different arbitrary function for each one of these different dependent variables. So good. So we're going to take this, plug this back into our integral. So good. So plug this back into our integral, and then basically go ahead and vary this path with respect to alpha again. So it's going to be equal to then the integral from x1 to x2. Again, we're going to have a dx due to the fact that we're treating that as our independent variable, sum over all possible I values. And then this is going to lead to partial of f, partial yi, minus d dx, partial f, partial yi prime, all times a to I, must be equal to 0, because again, we want to take when alpha goes to 0. Again, using exactly the same logic as before, all of these eta have to be arbitrary, which means that they all have to be some arbitrary value. We can't explicitly take that equal to 0. So in this case, what has to be true then is that what shows up again inside of this parentheses then must be equal to 0 independently, which means that we arrive at the new Euler equation, which says that the partial of f with respect to I minus then d dx, partial f with respect to yi prime, must all simply be equal to 0. So again, following exactly the same logic that we had before, the only thing that happens when I have more than one dependent variable is that each one of these dependent variables satisfies its own Euler equation. That's it. So basically, so again, if I had a y and a z, so I would have two different Euler equations. One would be partial with respect to y minus the derivative times partial with respect to y prime, and then I'd have an exactly the same one, but now with z's instead of y's. That's basically the only difference. So this has to be true again for all possible I values. So again, anytime I have more than one dependent variable, each one of those different dependent variables satisfies its own Euler equation. And that's it. So, nice and simple. Actually generalizes very, very nicely. So, the next complication we can run into then is, well, what happens if we start having constraint expressions? So what's a constraint expression? Well, in the last problem we actually just did, we actually saw constraint, even though we didn't call it constraint. And that constraint was the fact that, what? Since we're moving along the surface of the sphere, the radius had to be equal to rho, which was simply equal to a constant. Okay. So, in this case, we had this constraint equation. That's what we call constraint, or also what is known as an auxiliary condition, which we then apply to our Lagrangian. Keep saying Lagrangian, but to our integral that we want to our functional integral at which we want to evaluate. Right. So we have some sort of constraint that we want to place on here. So another way we could have wrote this constraint was we could have said that what? This was the same thing as r minus rho is equal to 0, or a better way of saying this is that this is equal to the sum over xi minus rho squared must be equal to 0. Okay. This is what we're going to call some constraint equation G. So in typical, our constraint equation then is going to have some sort of yi. So this is the constraint that we're going to put on our dependent variables, which depends then on x, and we want this then to be equal to 0. So here this is just saying that, again, the radius squared minus r squared then is equal to 0. But again, the radius squared is the same thing as all the different components squared together, minus that is equal to simply 0. So these are our constraint expressions. So what we want to do is whenever we have some sort of constraint, where our constraint is going to be of this particular type of form, right? So in this case, this is going to be in what we call an algebraic constraint. And we'll talk about what happens if we have a differential constraint. We'll talk about that in just a little bit. But we want to impose now these algebraic constraints then onto our functional integral, and then see what that does to our Lagrange, and to our Euler expression. So how does this thing actually change? So let's say that we have a simple case. We're going to write that f then is equal to f of yi prime x, which we're going to put as just 2. So we're going to write this as f of y prime, z prime, and x. So let's say we have this. So we only have 2 independent coordinates instead of multiple. So here we're then going to write our constraint expression as being g then, which depends on, again, this x equal to 0, which in our case then is going to be, this has to depend on y and z and x. So this is our constraint expression. And again, this must be equal to 0. Good. So basically, from here, what we've now seen then is what? So let's put this into our functional integral, and a variation of our functional integral, and see what happens. So if we do that, our variation of our functional integral with respect to alpha, then again, is going to be equal to the integral from x1 to x2. So again, our endpoints are still fixed. Integral dx, so then we're going to end up with, so I have the partial of f with respect to y, minus d dx of partial of f with respect to y prime. And then all of this is multiplied then by the partial of y with respect to alpha. And so this is the variation of y with respect to alpha, which we already saw before. This is after doing integration by parts. And then I get a plus partial with f with respect to z minus d dx, partial of f with respect to z prime, all times then partial of z with respect to alpha. And again, all this we want equal to 0. Now, so from here before, what we said was that, what? At least when I went through it quickly, I just kind of jumped the gun. Before, when I did not have this constraint, then these two things separated independently from each other because these two things were independent. But now what's happening is, since I have these constraint expressions make sure that these two things are actually now coupled to each other, which means that this expression here doesn't independently go to 0 from this one. Okay? So basically, anytime I have this constraint, because this whole thing has to be equal to 0, and this is both a function of alpha and z, where, again, these guys are going to be dependent both on alpha, these two terms no longer independently are, or not independent from each other, but they're now going to be dependent on each other. Which basically means, again, that this thing here doesn't separately go to 0 from this. So I don't end up with just that nice equation that I had before, but these two guys are actually going to be coupled to each other. So we have to then uncouple these guys from each other. So that way, when we set alpha goes to 0, these things are now going to independently go to 0, unlike they're doing here. Now, the way that we're going to do that is, let's consider the derivative of g. So using the chain rule, let's rewrite this then as the partial of g with respect to alpha times then d alpha. Okay. Now, since g, of course, as I erase it as I need it, depends on both y and z, I can then rewrite this then as the partial of g with respect to y, times the partial of y with respect to alpha times then d alpha, plus the partial of g with respect to z times the partial of z with respect to alpha, all then times d alpha, must then be equal to 0. So I'm just looking at the derivative of g in this case. Now, technically on here, g also depends on x, but the variation of x with alpha is simply equal to 0. So even though there is technically another term here that's the partial of g with respect to x times the partial of x with respect to alpha, x is independent of alpha, so x does not change. So in that case, that whole term is then simply equal to 0. Good. Now, again, what we know is that yi of x alpha is equal to yi of x evaluated at 0 plus then alpha times eta I of x. So now, when I take the partial of y with respect to alpha, then I'm just going to get what? An eta term here. So I'm going to get an eta y, and then when I take the partial with respect to this for z, I'm going to get an eta z. So this is going to become equal to the partial of g with respect to y times eta y, which is the y version of eta, plus and then partial of g with respect to z times then eta z, and again, all this must now be equal to 0. Okay. Good. So, basically using that, what that means then is that this term here is simply eta y. This term here then is actually eta z. But from this expression, we can see that those two things are not independent from each other. So from here, what we can do then is what? Replace one of those two, whether it be eta y or eta z. In this case, it doesn't actually matter. But we can replace those since they're actually coupled to each other from this expression. So let's do that. So this becomes equal to the integral from x1 to x2 dx then of partial f partial y minus then ddx of partial f partial y prime. So this one I'm going to keep the same, so we can factor that out at the end of the day. So from here, this tells me then that what eta z is going to be equal to then what minus eta y times then. So from here, I'm going to get the partial of g with respect to y divided by the partial of g with respect to z. Right? So here, now I'm going to pick up a negative sign. So I get a minus partial f partial z minus d dx partial f partial z prime. All 10 times. So again, I'm factoring out the eta at the end of the day. So this is now going to be multiplied then by partial of g with respect to y divided by partial of g with respect to z. And then all of this is going to be multiplied by, let me move that up here, eta x. And again, all this now has to be equal to 0. Oops, sorry, eta y, eta x. Now, again, since eta has to be arbitrary, what that basically means in this case is that whatever is inside of this square bracket here must be equal to 0. Since again, this guy's arbitrary, so I can't set him equal to 0. So since this is equal to 0, that means that this portion of the integrand must be equal to 0. So what that means then is that this term then has to be equal to this term. And let's do it. So this now tells me that partial of f with respect to y minus then d dx of partial of f with respect to y prime, all then times, so I'm going to bring the y term to this side, so this is going to be the same thing then as the partial of, so it's going to actually be divided, so I get the partial of g with respect to y raised to the -1, then must be equal to partial of f with respect to z minus then d dx partial of f with respect to z prime, all then times partial of g with respect to z to the negative 1. Okay? So, as we talked about when we talked about last chapter when it came to partial differential equations, what I have now is what? Partial derivative on this side, a partial derivative on this side, but since everything over here only depends on y, everything over here depends on z, what that means is that what? Each one of these two things must be independent of y and z, which basically means that this has to be some sort of constant, this also has to be some sort of constant, but since this has nothing to do with x and this also has nothing to do with x, that constant then isn't necessarily constant, it's at least as constant as far as what? Y and z are concerned. So this constant that it can equal to is actually a function of x. So just like we did with partial derivatives, we're going to say that this is equal to some constant. I'm going to call that minus lambda x. So that's equal to over here also minus lambda x. So again, since this only depends on y, this only depends on z, those two things have to be constant as far as y and z are concerned. But again, since there's no reference to x here, there's no reference to x here, that they can be dependent on x in general. Okay. So, what that means then is since this is equal to this constant, this is equal to this constant, then these two things are now independent from each other because they're now independently simply equal to constants. So finally what I get is, since this is equal to him, I'm going to multiply both sides by that, and then add it to the sign. So here I get the partial of f with respect to y, minus then ddx of partial of f with respect to y prime, plus lambda as a function of x, times then partial of g with respect to y is equal to 0. And then simultaneously I get another exactly like it, but in this case with z. So minus ddx partial f partial z prime plus lambda x partial g partial z must be equal to 0. So here, lambda x is actually what's known as the Lagrange undetermined multiplier. So this is the Lagrange undetermined multiplier. So basically, what has happened then is what? We have now gone from, when we didn't have a constraint, we had two independent variables, which basically means that we had to solve these, well, at least without these portions, but we had to solve Lagrange's equation, or Euler's equation twice, one for y and one for z, which means I had two unknown variables. Okay? But now what's happening is now I have three, because now I have this depends on y, this depends on z, so those were my original two dependent variables, but now I also have this lambda. So now we've increased the number of unknown variables now up to 3, but here we have two equations. We need at least one more equation. Well, that third equation is going to come from the constraint equation, right? So ultimately, I still have 3 equations with 3 unknowns, so I can actually solve this guy. So, in the general case, what's going to be true then is what? We're now going to have separate Euler equations, but each one is going to have a Lagrange multiplier attached to it. So in the general expression, so in the general case, we're now going to have a partial of f with respect to yi minus then d dx partial f with respect to yi prime plus the sum over j of then lambda j, which depends on x, times then the partial of gj, which depends on yi, must all be equal to 0. Okay? The j here just means that I can have more than one constraint. Okay? So here, gj is going to depend on what? Y, j, and x. And again, I need this guy equal to 0. Okay? So basically here what's happening is I have j number of constraint equations with I number of independents. So for example, I can go from 1 out to n, and then j can go from 1 out to m. So here I have j, or m number of independent constraint equations, and I have n number of different variables, which ultimately means that what? I have n plus m worth of equations that I basically have to solve. Right? So here, this one is going to give me a certain number of them, and then from the constraint equations, I'm going to make up the rest of them. So at the end of the day, I'm going to have, what, again, n plus m number of independent variables that I have to solve for, and then I have n plus m number of equations, because I'm going to have n number of equations from here, m number of equations from here, for my n plus m total number of independent variables, which gives me a number of n plus m different number of constraints. So, again, in the general case, I have this. Now, a lot of times, we're actually not given algebraic expressions for the constraints. We're actually given derivative expressions. So in this case, what's going to be different is that we're going to have sum of j of then partial gj partial yi. There we go. dyi equals 0. So in this case, this is our new constraint equation. So in this case, we're just giving a set of n number of differential equations to solve for, as opposed to n number of algebraic, or m number of algebraic expressions. So here we're just going to replace this guy with this guy. So here we're just told how this thing varies with a differential equation. But otherwise, it's, again, exactly the same thing. So here now we just know this term, so now we just have a differential equation to solve, as opposed to an algebraic expression at which we're given. Good. Now, another way we can actually be given a constraint is in an integral version. So let's talk about the integral versions of constraints and see what happens then. So let's say our constraint is actually an integral, which we're given as k of y is equal to the integral from a to b of our g of y prime x dx. So this is our constraint. So a good place that this might happen would be, let's say I want to find the distance between, or the path, which is the shortest between 2 points. But in this case, I have a total length constraint at which I have to meet as well. Right? So again, let's say here's point 1, here's point 2, and I need to connect these 2 points, but I need to do it in such a way that minimizes and keeps the length of this constant. Okay? So basically, I have a certain length at which this can happen, and I want to minimize this. So typically, the way that we're going to do this is we're going to rewrite this as the original functional integral plus some constraint, again, some lambda here, which is simply a constant, times this integral ky, which means that this is going to be equal to the integral from a to b of f plus lambda times g times dx. So, again, if we went through and we actually varied this integral by doing the same thing as before, so rewriting y as then being parameterized in terms of alpha, etc., etc. So if we did that, what we'd find in this case then is that the partial of f with respect to y minus dtx partial f with respect to y prime. So this is the usual Euler, plus then lambda times then partial of g with respect to y, minus then ddx, partial of g with respect to y prime. All of this then would have to be equal to 0. So this is the usual Euler. This is basically the same thing as the Euler equation now for g, but then we have this lambda term, which is the constant. So basically this would be the only difference. So now if I had a constraint, which is given by an integral form, again, we would just simply add this to the functional integral without the constraint, and now take the constraint, multiply by some sort of, again, Lagrange multiplier, which in this case would purely be a constant. And then in this case, we would have to then find the new Euler expression, which is now this one, which now takes that constraint into account. So again, typical problems this would show up would be something like this. So this would be the point A, this would be the point B. Problem like this is what's known as an isoparametric problem. So again, here, this has some fixed value of A, this has some fixed value of B. And then the constraint then represents a fixed value of length of the curve. So again, I'm trying to go from this point to this point in such a way that I have to fix the total length. So for example, if I wanted to connect this with a piece of string, where that string only had a finite length to it, then I have to determine how I would actually do that with this fixed amount of string. And again, one that's a minimizes the amount of area which I'm going to generate or something along those lines. So in the next video, we'll do a couple examples of these and basically see how this actually works.